各位来宾好，非常欢迎参加今天的活动。我们再等几分钟好不好？好，那请大家先休息一下，外面天气真的有点热哈。Give a brief introduction. Before my introduction, recruit people to join NtuEE or our society or in Chinese. 好，各位来宾好，非常谢谢今天来参加 Professor 马达瓦拉的演讲。那这是一个很有趣的 topic。这是 wireless， 而且又跟那个电动车跟 V2G 有关联哈。那我们待会如果演讲完之后有任何的问题，我们有 Q&A 的时间，好，那就请各位尽量发问。那 Professor 马达瓦拉他在这个工业界啊，也在学术界也都有很好的成就哈。OK， 那在开始之前呢，我想再跟各位讲几件事情，就是说是我们今天办的这个活动哈，是 NtuEE 的 Power Electronics Society 所支持的。那Professor Madawala 他是所谓我们有一个 program， 我们这个 society 有一个 program 叫做 Distinguished Lecturer， 就是所谓的杰出讲员。好，那这个杰出讲员呢，这个 society 就能够提供机票，让这个杰出讲员到我们这个不同的地方去演讲。那这个 Power Electronics Society 我们简称为 PELS 啊 ，P-E-L-S PELS。那在台北有一个 chapter， 那我现在是 chapter chair。所以各位比较有能够收到讯息呢，我们这次能够散发出去讯息的，大概就是我们 chapter 的 member 才能够收到。那另外一个呢，就是台湾有台湾电力电子协会，它的全名是中华民国电力电子协会啦，但是我们都习惯称它为台湾电力电子协会哈。就是我们也给这个会员呢，给这个讯息。那剩下呢，大概就只能靠亲朋好友啦，或者说有认识的大家这样传，所以传递的讯息算是有点有限。那如果说各位觉得像这类的演讲非常好，那你想要持续保有这个讯息的话呢，我们非常欢迎加入我们这个 society。那在外面的那个桌子呢，有一个那个加入 NtuEE 就是今年是半价，不过也是快到年底了。然后另外呢，我们还有一个 promotion code， 一个就是折价的码。如果已经是 NtuEE 的 member 的话呢，你现在要 key 这个码之后呢，你马上就可以变成我们的会员 for free。这是免费的，本来是今年。那明年的 一年也大概几块钱而已哈，大概10块啊这样美金的哈，所以其实是蛮值得的哈。所以在今天演讲开始呢，先跟各位说明一下我们今天演讲的典故支持。那也是因为 Pels 的支持，所以我们今天有机会邀请这个 Professor 过来这边给个 talk，right 好，所以也希望各位不管你将来不管是在学术界也好，或在业界也好，那随时能够有这个讯息的管道，对各位的专业领域也好，我甚至于说在不同的跨领域的 study 里面呢，我想应该会很有帮助 ，right 好。那接着呢，我们就来介绍我们今天的演讲的贵宾。那 Professor Udaya Madawala 他是在斯里兰卡出生，然后在那边拿学位，后来申请了大英国协的一个奖学金到 New Zealand 去拿这个 PhD degree。那很顺利的，他在1994这4年得到 degree。然后呢，在业界工作了3年之后呢，那1997呢就到Auckland 大学去任教，一直到现在。那 Professor 他有很多的paper，那他现在担任2个 IEEE 的 translation 的 associate editor， 一个是 IE Industrial Electronics， 一个是 Power Electronics，right？ 他在那边当 IE， 那在 society 非常活跃，他举办过PASC。就是我们 Power Electronics 在这个南半球办的会议南半球的 conference，OK， 包含澳洲啦、纽西兰啊、新加坡也算，然后巴西啊，这些国家 ，OK， 他还当过 chair， 然后他也获选为 IEEE 的 fellow，OK， 所以在学术上的成就的是非常好。那我们大家都知道说，纽西兰它几乎没有什么工业，我们会想得到就是观光。农业非常的好。那在比较欠缺工业支持的一个环境，那这个 Professor 还能够做到在学术上面，然后在电力电子上面，在这个无线传输上面都做得非常的好。所以大家可以想见，在这个比较不被看好的环境，但是能够有比较好的成就，这是一个非常不容易的事情。Okay, all right. Now I'm going to switch to English mode to give a brief introduction of yours. Okay. Okay. 好，那个 OK. All right. Thank you very much, Professor Udaya Madawala, and thank you for your coming. So before the talk, let's give a warm welcome applause for Professor's talk.
Okay. Can you hear me? Yeah, because I'm so used to teaching students in big classes, so I'm alright. And if I can't, first of all, I would like to thank Professor Chen for giving me the opportunity to come here. It was my pleasure to be here and on behalf of the Power Electronics Society. And my trip was the talk was funded by the IEEE Power Electronics Society. He gave me a very kind introduction in Chinese. I believe that he said all the good words about me. I didn't understand a thing, but nevertheless, I trust him. And also, I think Professor Chen talked about the Power Electronics Society. And how many of you are members at the moment? Can you put a hand up, please? See, still there are quite a few who are not members. So I encourage you to join the Power Electronics Society. There are so many benefits. In fact, I was going to talk about that, but given the time period, I got about 2 hours, but I decided not to talk 2 hours to bore you, and maybe I'll talk about 1 to 1.5 hours. And going back to Power Electronics Society, there are so many benefits, especially for students. I encourage you to join the Power Electronics Society because it's about $10 to become a student member, but what you get out from $10 is more than what you put in. For an example, you can go to conferences for discounted rate, and you can have the networking, you can understand and get all the information that is necessary, and what's the advanced technologies that's happening around in our electronics field. Especially for it to be very, very beneficial for your research. And also that there are scholarships that you can attend, and you can hear. Okay, and there are scholarships that you can apply for too. even for going for conferences, and the Power Electron Society subsidize your travel fees, so you can apply for the travel fees, and that's an incentive too. And just for a mere $10, the benefits that you can get is far more. So I really encourage you to do get the membership. Okay, so what I'm going to talk about is that, as you can see from my talk, wireless grid integration of electric vehicles for V2G applications. I'm pretty sure that you know about what is meant by V2G, and in order for us to do V2G, that you had to have bidirectional power flow, and that is you use the electric vehicle, the energy storage, as a battery, as an alternative energy storage. You store energy and you retrieve energy when you want to. So that's basically V2G. But in order for anyone to do that, you had to have bidirectional power flow. And what I've been working for last 10 years is about the wireless, how we can do wirelessly bidirectional V2G, the power flow. So before we talk about that, and let's have a look at why people are doing that. And as you all know that, and we know that increase in fuel prices and limited fossil reserves, and also environment pollution, these are major concerns everywhere globally. Everyone is talking about that. There are incentives, and everyone wants to go for electric, so cut down the emissions. So electric vehicles are everywhere. I would say it's sort of a buzzword, and everyone wants to go electric trains, electric cars, and electric bicycles. Everything is electric now. So as you can see that in some of the electric the vehicles, and mainly because that they can be regarded as the means of future transport. It's going to be the future transport, and they reduce pollution, and they enable efficient and clean transport, and also it's ideal for sustainable living. And in fact, if you want to be off the grid, all electric, and you can be self-sustained. And more importantly, and part of that is that we can use the battery storage or the battery of the electric vehicle as an alternative energy storage. And how we can use that, and that's the V2G concept. Now it has gone to a further level, and as you can see, this is the V2G concept here. As you can see, the power flow goes both way, from the battery to the grid or grid to the battery. And another aspect of that, or another version of that, is home to vehicle or vehicle to home. So you use the power the whole house using your electric vehicle. You use electric vehicle to commute as same as the same time you can use that to power your house, and that's a home to vehicle concept. In the future, it's going to be vehicle to vehicle too. And as you know that you have electric, you have the watches and the mobile phones now. Now the technology is such that you can transfer energy from one device to the other. And in future, and what they are talking about is that vehicle to vehicle, you have fleet of vehicle charging bay that you can exchange energy depending on the demand and how much you are willing to pay. So therefore, because of this reason, now it's called V2X. There is even called the V2 buildings, and how the whole buildings can be powered by using fleet of electric vehicles strategically placed. So that's going to be the future. So there are certain challenges, and we can talk about the electric vehicles, but there are some challenges, and the challenges are the increased power demand. And just for an example, if you take the UK, and the UK alone, there are 700,000 electric vehicles expected to be in 2020, and that requires an extra 500 megawatt of power. Where does it come from? So you can say that, yeah, we have reduced pollution, but it is the sort of shifting where the pollution takes place if you still burn fossil to get electricity. So this power has to be supplied, and how do we supply it? And there's a huge demand, and what time that you're going to do it. And then the charging rate, how fast you can charge. And as you know that all the electric cars, old ones, takes long time. You charge it whole night, and it will be available in the morning. Of course, that depends on the battery capacity. So how quickly that we can charge? Of course, now the future is going to be you can charge so quickly within 5 or 10 minutes. And there can be even up to 500 kilowatt chargers. And what's the distance per charge? And that's the range anxiety. One charge, how far can I go? So electric EV manufacturers and the battery, they are working on to improve the performance and also the battery capacity. So these are some challenges. And then substation, infrastructure. And just because we have electric vehicle, we have to supply, we have gas stations everywhere. Now, in order for us to enable electric vehicles to be used, then we had to have charging stations too. And who is going to give those ones too? So these have to be, so these are challenges in relation to the infrastructure. And then of course the compliance for electric vehicle charging has already been established for wired charging, and that is SAE and IEC. I will talk about that in a minute. And then frequency regulation, when this is all that demand is going to escalate, and charging, and how we are going to control the frequency, how can we regulate, especially at the distribution level. So what about the impact of on the grid? And I just talked about the infrastructure, but what happens when everyone, just imagine millions of cars charging at the same time, and how would it affect the grid? So everyone is charging, and then the more and more demand is going to be, but can we do something and optimize charging, this charging pattern? We can communicate and make sure that we are not going to overload the feeders, or the demand can be met. So, and these are some challenges and the impact on the grid. And this is just an example of that. And if you look at that on the left hand side, and without any, and how the voltage can be affected by charging. And this is somehow or other we can curtail it, or we can minimize that impact by optimized charging. Okay, so there are a lot of research going on, developments taking place, and to address these concerns, that how we can do it in more efficient manner. Many electric vehicles can be charged at the same time, but in an optimized manner, and also the minimum impact on the grid. Then the increased grid harmonics, and all these, of course there's a compliance there, but nevertheless more and more electronic components going to be connected to the grid. Now it's a different one, and earlier we had PVs connected to the grid and had so many issues. Now that we are going to connect electric vehicles, so there are some harmonics going to be injected into the grid, and how we can address these issues. And more importantly, whatever we do, it has to be efficient, reliable, and compact, otherwise no one will buy it. So what is important for an electric vehicle? Of course, I mean, that is obvious, but nevertheless, if you look at it from what is important is the grid interface in between the grid and the electric vehicle. It's called electric vehicle supply equipment. So it can be an on or off board. What it means is that in some can be mounted inside the car, some has to be mounted just outside. The reason being that some are so big, it's no point in having it mounted inside the car. Okay, so it's on and off board. So then question is that we have the electronic interface, whether it's going to be wired or wireless. Of course, the wired has been there for quite some time now. And as you can see, that's relatively simple, less infrastructure, and the standard has already been established, NtuEE70th, and in use at present. But whereas if you go to wireless, and as you can see, that it is robust, safe, convenient, can be used anywhere, ice, water, no problem, and it is all isolated. But there's a huge infrastructure change, and that's a challenge, and who is going to provide it? And also the standard still being implemented. I think it's more or less finalized, and as far as I know, it's going to be released early next year. And it cannot be used or deployed everywhere. Just think about that, the poor countries or the developing countries, everywhere they are using vehicles, but those are gasoline vehicles. But if you go fully electric, how we are going to support that infrastructure in these countries, especially in wireless charging? And the wireless charging is still in the development stage, but a lot of development is going on, and considering it as the future way of charging electric vehicles. So I'm going to talk a little bit about the wired integration before I talk about wireless, and just to give in context and what's happening at the moment. And this is, you can see, this is a standard, wired standard, and the SAE1772 or IEC is 61851. That's in Europe there, and you can go and get all these standards related to wired charging. So if you look at here, and here you can see the power level, and from the first row, and that you can see the level 1 charger. So obviously you can see the charge is located on board the vehicle, small, and the charging, it can happen either at home or office. And the supply is just a general outlet. You don't have to have a dedicated outlet as such. But you can see the power level is relatively low. What it means is, obviously, It takes longer time to charge. And of course that depends on the battery capacity, but nevertheless, for a given this battery capacity here, it takes closer to 2 to 8 hours, whole night. Then if you go to level 2, and that's a different level, and the power level much higher there, and there you can see that's about close to 20 kilowatts, and the charger can be single phase or 3 phase, and it can be a private or public outlet, and it has to have a dedicated electric vehicle supply equipment, because you can't simply charge it at that power level there at home. And as obviously you can see a reduction in the charging time on the last column, second column there, fifth column there. It's about 0.3 to 3 hours, but still it takes long time. You know that if you go to a gas station and you can quickly pump up, fill up your gas tank. Then we go to the next one now, and this is what a lot of people are working on, and this is the level 1 and 2 mode, and mode for DC charger. So this is completely DC. So DC, there is no AC to DC conversion there, so this is DC to DC. So you can see that the voltage, the charging voltage, and that is 200 to 100,000 volts, and the charging current can go almost up to 400 to 500 amps. So what they are targeting is now it's about almost to going up to 500 kilowatts. So I have some doubts. I think some are already working on that. Tesla is working on like 380 or 400 kilowatts, but it has to be an off-board charger. As you can see, it's commercial dedicated electric vehicle supply equipment. Someone has to pay for the service there. You can go and get that one charge so quickly, but you may have to pay more because this is sort of a commercial entity. And there you can see obviously the time is very, very small, quickly charged. But I still think that a lot of work or investigation is carrying on in relation to what actually would happen to the battery. The battery is taking that much of power within a so short period of time. And here you can see the level 1 charger, and this is the level 2, and this is the DC charger CHAdeMO, and that is the Tesla one here, as you can see. So the protocols, you can't simply charge just plugging in there. There are some protocols there, and there is some standard protocols, and this is the CCS, that's the combined charging system, and that is adopted by Daimler, Volkswagen, and BMW. And then the CHAdeMO, of course, from Japan, and that is Nissan and Mitsubishi and Kia, and this is one from GB and /T in China, and the supercharger, and that's in Tesla. So these are the protocols, and they comply with the standards that's been used at the moment for wired charging. And these are some of the charging connectors, and you have to connect the car. And as you can see that in the Europe and in the USA, what type of charging connectors that they use. And this is just a comparison of electric vehicles, and as you can see from here, and the EV type is the first column there. There you can see that the battery capacity and what sort of protocol that they use, and the onboard charger and how many kilowatts. And you can see that the Nissan Leaf is about 6.6, and the charging time from to full 100%, it's about 8 hours, a long time to charge. And whereas if you go down and to Kia, and that takes about 4.5, and therefore for Tesla it's about 5 hours. So but you can see that what is the price of that from here, and that is the kilowatt hour for 100 miles, and the range, how far they can from one charge they can travel. You obviously you can see that the Tesla takes about 417, and also the Mitsubishi Lander there. So these are some of the currently available electric vehicles in the market, and just a comparison of how they look like. About the global sales, and just to show then how much interest being generated because of these electric vehicles. So you can see the electric vehicles, and then the EV type, Nissan Leaf 2010 it was launched, and there are about 43,000 global sales 2017, and Tesla is about almost 45,000 Tesla. It's about Mitsubishi about 21,000, and the Volkswagen Golf is about 19,000. And in comparison to this, and the Chinese market is flooded with electric vehicles. So many electric vehicles used in China. So that's a little bit of an overview of the wired grid integration. So what I'm going to talk about is now wireless grid integration. Then we talked about the V2G system and the bidirectional EV integration. So from here you can see normally all wireless EV charging based on inductive power transfer or magnetic coupling. That is called the IPT technology. And as you can see that we have a grid, and the grid creates, and here so we have a converter here, it gets a very high frequency, and this is sort of a pad. It is mounted on top of the ground surface there. So what actually happens is that car comes and parks on top of this pad there, and there is another pad that is mounted underneath the electric vehicle there. So, and this grid from here, it generates a high frequency current, it creates a high frequency magnetic field, and that magnetic field coupled to the another coil, and which is called the pickup coil or the secondary side coil, and then the energy transfer takes place through magnetic coupling here. So this is, as you can see from that arrow, it's only the one-way power flow. So I've been working on for some time now, quite some time. I started first to do this one, and how we can have the bidirectional energy flow wirelessly. So that's my talk is more about. And to have a look at the typical system of the electric vehicle charging, and as you can see from here, here's the grid. You get the 50 Hertz, and we have a converter that will convert it into a high frequency signal or high frequency current, and the frequency is set to 85 kilohertz by the standard now. And then we have a compensation circuit which we actually need. Without that we can actually efficiently transfer power. I will talk what is meant by that. Then we have this magnetic coupler. It's called the charging coil that is mounted on the surface of the road, and then it creates a magnetic field, and that magnetic field is again coupled to another coil here that is mounted underneath the vehicle. And then we have a compensation circuit. I will explain what it is. And then we have another converter that conditions that, and that is fed into the battery. So this is a typical electric vehicle wireless charging system. And this ground, and this part here is the stationary part, and that part is called the ground assembly, and the one on top that is called the vehicle assembly. So if you now read some papers, so if you go to standards still being prepared, and you can see that the GA and the VA, and that refers to ground assembly and the vehicle assembly. So there are some challenges. The first challenge is the how do we charge, and the stationary or both stationary and dynamic. So what it means that when the car comes and parks, that is okay, and still there are some issues and how we do that, and because we had to have a proper alignment. You can't have perfect alignment between the two pads. And also, if it is stationary, can we do that in dynamically? And that means the car travels in dedicated lanes at 100 kilometers per hour, and that's what the future is going to be. And can we charge and send impulses of 20 kilowatts, and within about 40 milliseconds, and we can generate that pulse, absorb it to the battery, and that's what the future is going to be. So the car goes at 100 kilometers per hour, and it goes over some pads and buried underneath the road, and it sends pulses all synchronized, and the car gets charged, and that's going to be futures. But there are some challenges, how we generate, how we absorb. And then we have what's the direction of the power flow. You need bidirectional, and the bidirectional one is the one that is required, that you can have active control, and also you can have V2G. Then the controlling power converters, it's not as simple as the normal power converter. Main reason for that is all wireless power transfer systems are high order resonance systems. So they have some compensation, series, parallel, series, parallel, series, different compensation strategies, and I will talk in a minute, in order to have efficient power transfer. So having a high order resonance system at 85 kilohertz, controlling is not that easy. And then magnetic pads, and how do we design, what is the size, what's the cost, what's the weight, these are issues. And how do we contain the magnetic field within safety limits, and how do you make sure that it will attenuate to a certain level within a certain range. So those are challenges, and many have been working on that, and accordingly they have designed very efficient pads, and these are different types of pads, and you can read about that, and the circular pads, solenoidal pads, and DDQ, and bipolar pads. And Oakland University, Professor John Boyce and Kovic, and they have been working on this for quite a long time too. They have come up with different pads, and obviously some others from different parts of the world too, and propose and design different pads, and they are all patented. Then the communication between the vehicle assembly and the ground assembly. So you have to make sure that, and the car comes and parks, and then only that you can charge, because there's a magnetic field going through, there's a safety concerns there, so you had to have a communication. And more than that, if you want to have active control with bidirectional power flow, you had to synchronize the ground assembly with the vehicle assembly, both sides, to make sure the power transfer takes place either from the car to the grid or grid to the car, the vice versa. So that's very important, and they had the synchronization and also the tariff, and how to make sure, how to control the energy flow. Then the compliance. Even if you build all these things, what is most important is the compliance, and that is related to safety, EMFs, radiated and conducted emissions. So normally these are all now specified, and whatever the pads that have been designed and proposed and then been implemented, they comply with the standards here. Then most important is you can do all these things. Then the physical construction, the cost and the size and the weight and the robustness, it has to be compatible with the wired charger, otherwise no one will buy it. So that is what the goal is. If the wireless charging too, it's very similar to a wired charger. So the standards and the wireless charging and the standards, it's being implemented. I think it is more or less finalized. As far as I know, it will be signed, the standards. The car manufacturer, the University of Auckland, next year in I think January or February, and that is called the J2954 standard, and it stipulates all related to wireless charging, and the safety, performance, interoperability, and the communication control, and also the EMF and exposure, etc. And J2954, that's for the LDEV, that stands for the light duty, and there's another standard for heavy duty, and J2954/2. So EVs are expected to be, if you're charging with wireless charging, if something happens, you must be able to charge by wired means too. So that is what it says, that it has to be compatible with J1772. So the frequencies the frequency is just set and to 85 kilohertz, and there had been big debate